Hey everybody, in this video we're going to talk about arc length. So thinking back to what you saw previously in single variable calculus, if we've got some curve, we're considering some portion of an arc. If we look at some small piece of it, or we denote arc length by s, if we look at some small piece delta s, then we see that we can use the Pythagorean theorem to approximate delta s in terms of some change in x, delta x, and some delta y. And we know that as we take smaller and smaller pieces, we zoom in more and more, that portion of the arc that we're looking at gets straighter and straighter, and the limit as we shrink it down to, say, delta x going to 0, we get the statement about differential ds in terms of dx and dy. So with that statement, we can do a little bit of algebraic rearranging. We can factor out dx squared and then bring that outside of the radical. And so we have the infinitesimal increment ds in terms of dx and dy that looks like this. And so then we can find the arc length from some x value a to some other x value b just by evaluating this definite integral. So that was what we've seen before. And looking at, instead, considering a vector valued function, things look a little bit different. So to note at the beginning, if the x component of our vector of our point on our path is given by the value of the function of its x component, in this case say f, then a little abusive notation gets us an expression for the infinitesimal increment dx in terms of the derivative of f and increment in t dt. And we get something similar for dy in terms of the function for the y component g. And then if we look at our infinitesimal increment ds in terms of dx and dy and apply what we just saw, and do a little bit of rearranging again, square some pieces out, group the dt's, factor, and pull that outside the radical, then we have our infinitesimal increment ds in terms of the component functions of our vector valued function. And note that we could just as easily do this for a vector valued function in higher dimension, 3 dimensions. There would just be maybe, say, some function h as a z component, and we'd get a similar looking result. There'd just be a plus h prime squared under the radical. But that piece left of the dt is just the magnitude of v, the magnitude of r prime. And so if that's what ds is, then we can just integrate to find arc length s. And that is, so from some t value a to some t value b, the length of the arc traced out by a vector valued function is just the definite integral of the speed, so the magnitude of the velocity, the magnitude of r prime. And if we want, we can also generate an arc length function. That is, instead of integrating from some constant to some constant, we change the variable in our integral to u to avoid confusion, and instead integrate from some constant up to a variable t. That'll give us a function for t, a function of s in terms of t, rather. But the fundamental theorem of calculus tells us then that the derivative of s with respect to t must be v evaluated at t. So we see a result that hopefully isn't too surprising. That is that the rate of change of arc length is given by the speed at any point. So consider how fast a particle is moving along some curve. That is exactly how fast the arc length is changing that you're sweeping out at that point. Okay, so let's look at an example. Take a moment and see if you can figure out the length of the arc between where the parameter t is 0 and the parameter t is 2 pi for this helix that we've considered before. That's sort of corkscrewing up the z-axis. A little bit of calculation shows us that the magnitude of v, the magnitude of r prime, is just root 10. It's a constant in this case. And so to find the arc length between 0 and 2 pi for t, we just integrate, and we end up finding that the arc length specified is 2 pi root 10. I'd like to take this example a little bit further and show one more thing that we can sometimes do, and that is if I take this vector valued function and consider the path that it's tracing out, we can make that arc length function by integrating from some constant to t. And so now we have a relationship between arc length s and our parameter t, but what that allows us to do is express t in terms of arc length s, and then we can make a substitution back into our original vector valued function to instead switch from having our parameter t to having this different parameter s. So we've reparameterized our vector valued function in terms of arc length. What that means is from some starting point, instead of t just sort of being an almost arbitrary parameter, now I've got s, and when I consider an s value of, say, plugging in an s value of 2, what I'm saying is, starting from my starting point, that will take me to the point where I've gone an arc length of 2 units along the path from that starting point. Or if I want s to be -3, I want to talk about going 3 units in the other direction. Or if s is 10, I'm talking about going forward along my path 10 units. So sometimes it's a nice way to express my vector valued function parameterized in terms of arc length. It makes a lot of things a lot simpler. One thing we can consider is what's going on with the speed. And so I'd like you to tell me what's going on with the speed of this vector valued function if I'm integrating, or if I'm differentiating with respect to my new parameter s, which is arc length. So take a minute, think about this one, see what you can come up with, and we'll talk about it in class.